Good afternoon, everyone. Welcome to the Bradford Speaker Series. I'm Elke Weber. I'm the Gerhard Einlinger Professor of Energy and Environment and also Professor within C-PREE. And it is my pleasure today to introduce Professor Anders Levermann to be our speaker. Professor Levermann received his PhD in theoretical physics in 2003 at the Weizmann Institute of Science in Israel, where he worked within statistical physics. Then afterwards, he moved to the Pottsdam Institute for climate impact research in Germany, initially as a postdoc. And since 2008, he has been a senior researcher there. He's also now professor of dynamics of the climate systems at the Physics Institute of Pottsdam University in Germany, and affiliated with Columbia University as a visiting scientist. He has done fundamental research on things like sea level change, paleoclimate, ice sheet modeling, but today he will talk about a different line of research, in particular on the effects of rainfall changes on economic production that is based on a paper that was just recently in January published in Nature. So please, Anders, take it away.
Yes, thank you very much. Thank you very much for this opportunity to speak here today and to tell you a little bit about my research. I slightly expanded the title from what was advertised to towards estimating the costs of climate change, simply because we did a few other studies recently that I think can be brought together towards this estimation of the costs of climate change. One part being the effect of rainfall on economic production. This work was really carried out by a number of people, most notably Maximilian Kotz and Leonie Wenz, who did most of the work together with me, and then but others, Sven Willner, Christian Otto, Matthias Kalkuhl, an economist, and Stefan Lange and Annika Stechemesser. The costs of emitting carbon is a very important quantity to compute and to estimate for the future. And why is this important? Well, there are a number of reasons, obviously, but if we just look at climate policy, then there are regions around the globe where carbon already has a price. You can see here the different kinds of systems. Some have carbon taxes, some are leaning towards a carbon emission scheme, a trading scheme. And especially in Europe, you can see that there's a carbon emission scheme already operating. And you can, in addition, some of the countries have carbon taxes. And I'm just putting this out here to show you that there's, first of all, a lot of space on the planet where carbon doesn't have a price yet, but also to give you an estimate of how much the emission of 1 ton of CO2 costs currently in different countries. And you see values here from 15 euros, that it would be, well, it's a similar amount in US dollars, obviously, and well, to more than 100 US dollars or euros in Sweden. Well, it's US dollar and euro are not the same anymore, but still, the order of magnitude tends to hundreds of US dollar. And the question is where does this number arise from? And it arises from either a trading scheme where the amount of carbon that can be emitted from within a year is being set for example, in the European Union, and then slowly reduced from year to year. And the market is simply determining what the price is. Another way to, if you put a tax on carbon, another way to motivate this carbon price would be via the damages that the emission of carbon dioxide causes. And to this end, a long time ago, there has been a number defined that's called the social cost of carbon. And you can see here that it is generally computed as the change of the damages due to a change in the global mean temperature. And then the change of global mean temperature you get for adding 1 ton of CO2 into the atmosphere. Now you have to add this value up over time, and generally because economists generally like to discount things, saying that future emissions are past emissions are less important than future emissions. You have a decay or discount ratio here. So you multiply everything by e to the minus d times t. This is a multiplication, it's not delta t. And you sum this up over all time into the future. So this gives you basically the additional costs that 1 ton of CO2 is causing in society. Now, this is difficult to compute and to estimate for the future, especially because we don't know how what kind of adaptation measures we will come up with in the future, and so on and so forth. But there are a number of ways to try to estimate this. And I just want to highlight here briefly, it's going to be about one line of estimations that come from empirical estimates, from observations of past relations between climate and the GDP in different regions, or the regional gross domestic product. But I want to highlight that there are other ways by which one could compute the costs of carbon, and these are process-based. And I'm saying that because in climate physics, or in physics in general, this would be closer to the hearts of many people, so-called process-based approaches. And we have developed I think in 2012, we have developed an economic shock model, if you like, which is trying to track the weather shocks along the economic network of the globe. To this end, we used the observed economic structure on the planet. So how much of one good is produced somewhere and then transported to another place on the planet, where it is then used as for production of another quantity. So this kind of network yields a complex network, obviously. And we have added in 2017, it was published, took us quite a while to develop this model. We have added an economic shock dynamics, where each of these knots here, each production side is given here in the center, has inflows from other production sites, and then tries to optimize its production myopically, meaning in one moment, without knowledge of the world around it, really, just living in the moment, if you like, tries to optimize its production based on the estimate for how much it can sell its product and how much the market tells it the production materials cost. So this is a local optimization, and the whole idea here was not to use intertemporal optimization in order for the system to be able to be surprised by weather extremes. And I just want to show you, this is how this would look like here. You can see, for example, a simulation of the flood events on the planet, and then the economic response. So whenever there's a dot lighting up here, this is a flood event, and then you see the color. This is the response of the total losses on the planet, and you see that it's not always the direct impact that's most relevant. It's sometimes just the repercussions of this weather extreme in one place along the supply chains globally. So this is one way to compute costs of climate change, costs of weather extremes, but this cannot be comprehensive. We can make statements here. You can see, for example, publications on the effect of the flood risks on the left-hand side. And then we can make statements that are qualitative in nature, in the sense that that we can say the economic risk, for example, of weather extremes are imported from other countries, for example, from China. If you have an increase in flood damages in the next 20 years in China by 80%, this is our estimate. And if no adaptation measures are taken in the next 20 years, and this would be then exported to the US and also to Europe, but due to the equilibrated trade balance of the European Union with China, Europe can actually compensate for these damages while the US cannot. These kind of qualitative statements are possible, but we don't dare yet to actually compute quantitative values for the costs of these weather extremes. And that is why we use an empirical approach to estimate the social costs of carbon. This has a number of advantages and a number of disadvantages. And we are obviously not the first to do this. There have been a number of studies by Melissa Dell and colleagues, but there was a big breakthrough when Marshall Berkey and Solomon Zhang and Edward Miguel published their paper in Nature, where they correlated non-linearly, where they correlated the change in the annual mean temperature on a national level with the changes in economic growth. And what they then assumed was that there is that this is a growth effect, in the sense that if the temperature changes by a certain amount, this will lead to an economic growth reduction or to economic growth increase that persists over time in this region. And this led to very high estimates of the social cost of carbon for this century. We have now taken a similar approach, but have refined it in a number of ways. And the first path is going along the temperature line. So what Berkey et al. Did was use the annual average temperature in a given region and find a relation using a standard correlation. And I will show you in a minute how this is done. And this is a standard procedure in econometrics. We also use the same, but it's annual mean temperatures in a specific region on a national level. What that means is that, for example, if in the US there is a hot summer in the West, and a cold summer in the East, then this will be averaged out, and the impacts on this regional level, on the states level, will also be averaged out, and you're losing a lot of information. To this end, Matthias Kalkuhl and Leonie Wenz published in a relatively high economic journal this updated data set on the regional gross production, the RGP, for much finer resolution on the planet, and use this to estimate the future impact on the social costs of carbon. You can see here with this high resolution, and they have this data for the last 40 years. This is what we are using. That's why I'm highlighting this here. Matthias Kalkuhl is at the University of Pottsdam, and Leonie Wenz is with us at the Pottsdam Institute for Climate Impact Research. You can see here now we can actually distinguish the different regions that are physically relevant, that are climate relevant, because we are now at a regional level that is able to capture what a weather system would be like. A weather system has typically the regional extent that is finer than the national level, and this can now be captured by this analysis. So the first work. The first work that we did, I'll come to this in a minute, is reproducing the Berg et al. Data, and also putting it on a higher level with respect to the variability in temperature. But let me first highlight that even with the annual average temperature approach and the national level of the economic data, you already get estimates for the damages that brings the economically optimal temperature increase into the region of the Paris Climate Agreement. We published this paper saying the Paris Agreement passes the cost-benefit test. And what we did, and the reason for this is very simple. It's highlighted here on the left-hand side. It's really, we did something a bit more sophisticated. We used the DICE model and did a global optimization procedure and so on and so forth. But you can see why the 2 degrees of warming actually becomes very easily the optimal warming of the planet, economically speaking, if the damages are getting high enough. What you see here in this graph is the current, on the x-axis, the temperature increase on the globe. And you can see here the current warming level is around 1.1, 1.2 degrees. And on the y-axis, without any units, you see cumulative costs. And the mitigation costs are by definition, they're given here in green, they are by definition 0 for no mitigation, which gives you about 4.5 to 5 degrees of global warming by the end of the century. And they increase if you set your warming level, your desired warming level, lower and lower. And they have to actually get to basically infinity at the current warming level. Now, the total costs, the macroeconomic costs of climate change are the sum of these mitigation costs here and the damages, which are given here as the black line, just as an example. We put it linearly here. And the sum of the two are the red curve that you can see here. These are the dashed and the dashed and the pointed line here are just, the dotted line are just the different parameter settings. But you can see immediately the moment you have enough damages, you're pressing the optimal, the minimal costs, which is given here as this crossing, you press this against the current warming level. Because there's a wall of mitigation damages on the left-hand side, but also a wall of damages due to climate change on the right-hand side. And that's why it's not surprising that no matter what the socioeconomic assumptions, also the preferences for, how much you value the future, how much you value the future generations' welfare, independent of these quantities, you get around 2 degrees of global warming as the economically optimal warming level of the planet. And that's obviously only given the fact that we are already at 1.2 degrees, right? It's not to be confused with an actual optimal warming level, which would probably be 0 degrees, because it would mean we are not perturbing the climate at all. But we are already at 1.2 degrees, and there are mitigation costs if we want to and have to reduce the emissions, the carbon emissions on the planet to basically 0. But now let me get to the costs of emitting carbon and the empirical estimates that were started by a number of people and which really made a big step with the Berkey et al. Paper. But the Berkey et al. Paper, as I said, and the Calcul and Vance paper also, and a number of papers, they used annual average temperature on the different regional resolutions. The first thing that we did, we looked into the variability of temperature, because all of a sudden, when you have this kind of high resolution in space, you can think about weather systems really, and you can ask, how is a sudden change in temperature from one day to the other affecting climate? You can see here 2 examples, one in Argentina and one in Mexico. These are the temperatures, and they both the temperature over a year, and the daily temperatures, and you can see they have both very similar annual mean temperatures, but the variations with both the seasonal cycle in Argentina is much larger than in Mexico, and also the deviations from the monthly mean, the daily deviations from the monthly mean are also much stronger in Argentina than in Mexico in these examples. So this is what we wanted to explore. and did so, and found that there's an independent contribution from the temperature, from the day-to-day temperature variability to the economic growth in a region. Then we looked at how this changes under global warming. We found that the observed pattern of temperature variability is reproduced. It looks like this in the two different observational data sets that we looked at. Well, no, left is the observational data set from NOAA, and on the right-hand side is the modeled response. You can see this in a number of different models. On the right-hand side, there is a very similar pattern in the observations and in the climate models with respect to the day-to-day temperature variability. And this is actually very encouraging that you find this kind of system, or this kind of pattern that is robust, because we are talking about weather now. The climate models are meant to reproduce the climate of the planet, and thereby do not necessarily have to be good on a weather level, on a day-to-day temperature variability level, but they turn out to be reasonably, they turn out to show the same pattern of day-to-day temperature variability after some bias correction, statistical bias correction. What we find in this study, which was only really a purely physical study, there's no economics here, that this pattern actually increases not just with the global mean temperature, as we can show here, and which we show in the plots, but also with the rate of warming per decade. So the speed with which the temperature is increasing, and that is quite something. And we haven't fully explored this to the all the way to the end, because it means what you would think intuitively is true, that the weather becomes more and more extreme, more variable if you increase the temperature of the planet quickly. But it's counterintuitive to a meteorologist in a sense, because there is basically no memory in the atmosphere. So it shouldn't really matter whether you increase the temperature of the planet fast or slowly, because the atmosphere equilibrates very quickly. So my guess is that this is actually the origin of this fact that you see here in the scaling of the warming rate is actually in the ocean. But that's on the side. Let's go back to the economics, because the exercise that we did for the temperature variability, we did now for precipitation variability. And here I will now really go into the methodology, and then you can understand how we actually did it also for the temperature variability. But I want to highlight here the precipitation variability, because it's the most recent paper, and it's also very, very interesting because it shows, I think, sorry for saying that, but because it shows that, yes, it is what people think what disturbs our economy, and that is weather extremes. Weather extremes are obviously disturbing our way of life and thereby our economic life. We can see this in extreme rainfall events, in storms. We just in Europe, we just had a very strong storm. This flooding that you see here on the left was in Germany last year, where we had a very strong flood event with a lot of damages. But economists generally say, well, if you destroy something via a typhoon, a hurricane, a tropical storm, a mid-latitude storm, or precipitation, or even heat stress events, when you destroy something, you can rebuild it, and it's generally or very often good for economic growth. So independent of this, that it's generally good for the economic growth, you can find the effect of extreme rainfall event and thereby of damages in the economic data as a negative contribution to the economic growth rate. But, and that is interesting, this is here how we looked at the extreme rainfall events, and I'll explain this in a minute. But what I want to highlight is it's not just the destruction that occurs due to extreme weather events that is relevant. It is any kind of unforeseen perturbation that slows down our economy. So there's extreme rainfall that has an impact, but also the pure number of the number of rainy days that has an impact. And I'll show you, I'll show this in a minute. Here again, an example, as I showed you earlier, two regions, Austria here and Vietnam on the right-hand side, with very similar total annual rainfall, but very different distributions in the rainfall per day. A much longer tail in Vietnam when it comes to the rainfall, the daily rainfall distribution. So what did we do in order to estimate the effect of this precipitation, daily precipitation, onto economic growth? Well, first of all, we looked into the historical climate data, and from this derived different measures, climatic measures. One is the annual mean temperature that I showed you earlier. Another is the annual mean daily temperature variability that I also showed you earlier. But in this study now, we derived 4 different rainfall measures. And then we aggregated these spatially to the subnational level of the calcul and events of the economic data in order to be able to compare these, and also to aggregate this onto an annual level temporally. So even if you have if it's about the daily temperature variability or the daily precipitation on rainfall variability, you want to have a measure for this on an annual scale so that you can compare to annual economic data. And then we did a standardized fixed effects panel regression model to assess the effects on economic growth. So on the left-hand side, you see here the change in the economic growth rate. It's generally given as the difference in the logarithm of the regional GDP, GRP, per capita. And that depends on the region that you look at, which is not a country anymore, but for example, a US state or a Bundesland in Germany or province in China, and a specific year. And this can now depend on the temperature variability and the rainfall variability. And we assume this is linearly dependent on one of these climate quantities, which we have aggregated onto the regional level. That's why there's an R here, and onto the annual level. That's why there's a Y here. What we also take into account, and that is very important, but is also standard in econometric analysis, these are so-called fixed effects. Here we have this mu of R, which takes account of all the regional effects that do not depend on climate and also not depend on the specific year. That accounts for the differences in the economic situation in different regions on the planet. And then we also have a fixed effect eta y here, which accounts for something that happens globally in a year. But for example, as the financial crisis in 2008 and 2009, which has an imprint everywhere on the planet and does not necessarily depend on the region. And then there's also the eta term here, accounting for the mixed effects, which are not climate related. Now you can put this alpha times one of these quantities, but you can do plus beta times another quantity and so on and so forth. And that's what we did. And to this end, we investigated the annual mean temperature of the region, the annual mean daily temperature variability, plus 4 distinct effects of rainfall on economic growth, which we found to have significant contributions. We checked many more quantities, but these four had pronounced and statistically significant contributions to the economic growth rate. First was the total annual rainfall. And you can see here the formula for that, if you like. Unsurprisingly, the total annual rainfall, actually, if it increases, this is the change in the marginal effect on the economic growth rate in percentage points for one standard deviation increase in the total annual rainfall in the specific region. And you see that it always has a positive effect on economic growth. So more rain, annual mean rainfall, actually means more economic growth. This is a little smaller when you are already in a region where there is high total annual rainfall, and it's more strongly pronounced in regions where you have very little rainfall. This is basically the agricultural effect. I have to speed up a little bit. The number of wet days was the first daily measure that we investigated. And this really just counts the number. The H here is always the Heaviside function, which is the step function. It's 0 when the argument is smaller than 0, and it's 1 when it's larger than 1. So we count basically all the rainy days that have more than 1 millimeter of rainfall, which is very little. So it's basically just the error filtered out. And you find here immediately that this has a negative effect everywhere on the planet. If you increase the number of rainy days, then this has a negative effect. And the negative effect is generally stronger than the effect of the total annual rainfall. And that sounds almost like a contradiction. So if you have more rain, that's good. If you have more rainy days, that's bad. It's a very simple, way too simple way of saying it, but I want to highlight here the counterintuitive effect. We also looked at extreme rainfall data, where we looked at the 99.9 percentile and summed up the rain that falls within this 99.9 percentile in the region. And we found here also a negative effect if this extreme rainfall measure increases. When the annual mean temperature in regions where the annual mean temperature is higher, this actually becomes less of an important effect. But in cold regions, the extreme precipitation effect has a very strong effect on the growth reduction. And last but not least, we investigated the deviation from the monthly mean rainfall. It's a bit more complicated here, but here again, if you have a decrease in the monthly rainfall, then this is associated with a drought, a dry month, and that is bad for the economy, to put it very simply, while there is a small positive effect if you have more monthly rainfall, which is also more complicated. It's quadratic here. Now, if you now put this together and look at it on a regional scale, on a global scale, region-wise, you can see for an increase in annual total rainfall, you see a positive effect onto the economic growth, basically everywhere on the planet. And we know that under global warming, the annual total rainfall generally increases, but not everywhere. There's a pattern associated with global warming or for the total annual rainfall. The same holds, the reverse holds for the number of wet days. When you increase the number of wet days everywhere on the planet, you have a decrease in economic growth. And non-surprisingly, but perhaps surprisingly, even smaller effect is when you increase the extreme daily rainfall. The monthly rainfall, if you decrease, it's a negative shock that is shown here, then you also get a decrease in economic growth. And that's also uniform. Well, it's not uniform, it's not homogeneous, but it has the same sign everywhere on the planet. If you look into the different, if you want to understand why this is the case, it's helpful to look at different regions. And here we only dare to subsample the poor nations and rich nations, so just two different sets. And you can see that the extreme rainfall actually has a similar effect on rich and poor countries. The number of wet days, however, has a much stronger effect onto the rich countries. It has a stronger negative effect on the rich countries than on the poor countries, and while the others are similar in magnitude. And that already highlights this point that I wanted to make earlier, that it's not really the destruction that is the most exciting thing for me, at least, that is perturbing our economic growth here, but it's the sand in the gear, if you like. It's the deviation from what we are generally used to. So if you have a change in the number of wet days, then and the associated rain that you get is actually good for the economy. But the fact that you have more rainy days is bad for the economy. And the fact that this is shown more strongly in rich countries indicates that it's really these countries that are highly optimized in their economic flow, in their in the transport sector, in the transport and in the interlinkage between the different economic sectors, that gets out of balance and that is producing this perturbation. And you can see here on the right-hand side that this is actually the case, because in the number of wet days, you find a strong difference between the service sector and the manufacturing and the agricultural sector. So the extreme rainfall and the number of wet days, both daily measures, both have very little impact on the agricultural sector, while they have, especially the number of wet days has a very strong impact on the manufacturing and service sectors. I want to round this up now. If you look at the physical changes under global warming, and we'll do this next, and in order to really be able to project this into the future, then you find in all these different measures very complex fingerprints of global warming. So you cannot easily say that the number of wet days increases everywhere on the planet. You can also not say that the global mean, the annual mean precipitation is always increasing everywhere on the planet. There are distinct fingerprints of global warming. But what you can actually find is that with the global mean temperature, these patterns that you find are always increasing for the mean precipitation, for the number of wet days, for the extreme rainfall, the monthly deviation, and the extreme rainfall. So you have a distinct pattern, and then you find that this pattern increases with the global mean temperature change. And you can actually, well, this is again a purely physical study that we just submitted to the Journal of Climate. This is actually very, very interesting because you can compare it to fundamental physics, Clausius-Clapeyron relation with temperature. That's the amount of water vapor that you get that you can get into the atmosphere in a warmer atmosphere. So in conclusion, and I hope I was not too confusing, is first of all, I want to make a statement that is clear, and I just want to make it again. I didn't really show this in this talk, but it has to be clear that in order to stabilize the temperature of the planet, we need to get to basically zero carbon emissions. That's something that people don't have in mind very often. But since the half of the CO2 that we emit into the atmosphere stays there for a very long time, and most of it stays there for as long as we plan our society into the future, which means it's basically forever. Stabilizing the temperature of the planet can only be achieved by basically zero carbon emissions. For any temperature target beyond 2 degrees, climate change is more expensive than climate mitigation. This has also become clear. We did this one study that I showed you, but there have been a number of studies by Moore, for example, in I think she's in Stanford now, and other brilliant studies that looked at this from all kinds of angles. You are hitting the mitigation wall on the left and the climate damage wall on the right, and that's why you cannot afford to go beyond 2 degrees of global warming. A new step now that we propose is to account for variability in the temperature and also in the precipitation in climate variables altogether, because they generally increase the cost estimate for climate change. We haven't made the full calculation yet. We will do. There's also an important, discussion necessary on the depreciation rate and other socioeconomic or other societal assessments, or how you call that? Well, but there's generally an increase in the costs. And it's not, and that's something that I would like to highlight. It's not just the extreme events. It's not the damages that are caused by the temperature and precipitation extremes, but it's in general the hindering of economic flow and prosperity by unexpected events, by changes from what we are used to, that are already strongly in changing our economic growth, and will do so in the future if we don't take climate change seriously. Thank you very much for your attention.
Thank you so much, Anders, for a really, really interesting talk. It's chock full of interesting models and results. And we have a few questions. Also, I want to just encourage everyone to type your question either into the Q&A or into the chat. I'm monitoring both, and I will call on you to ask your questions. I think the first question from Saverio Perry actually sort of gets to the last set of results that you discussed. And I think sort of your main takeaway from those analysis is the level is really in the details, right? We can't look at just annual changes in rainfall and come to any conclusions, because it's sort of how the rainfall happens and for what sectors it happens, and one set of conclusions doesn't necessarily generalize to the other ones.
Yeah, I see I see also the comments here now. Yes, I mean, but what's really interesting is that there is actually that you can find in the economic data of the past 40 years, and I didn't mention that really. It's more than 1,500 regions on the planet for the last 40 years, and you can find statistically significant signals of climate change of all 4 of these precipitation measures in the economic growth of the region, which was quite surprising to us, because there was a good reason why people started with annual average temperature, because they thought, well, 40 years, the economy is changing so much due to other causes, obviously, not just temperature. Let's hope we can find a temperature signal in this, right? Mm-hmm. So then we were surprised to find a temperature variability signal in all of these regions, which was only possible because we had this higher resolution economic data. And now we find a temperature signal in all 4 precipitation measures. And that kind of shows that there is actually a universality behind this, mm-hmm. that there's actually a specific way of how the economy responds to changes in these quantities. And that is more more days of rain make the economy go slower. Mm-hmm. More extreme rainfall makes the economy go slower. That wasn't so surprising. More rainfall altogether makes it stronger because of agriculture. And the deviation from the monthly mean is really has two sides. If you have less monthly mean rainfall than you expect, then you get a drought, and that's bad for the economy. If you get more, it's a bit better for the economy.
Mm-hmm. Saverio, do you want to follow up and ask your question?
Hi, thank you. Yes. Yeah, I was just wondering, Elke already explained my point of view, my question. I was wondering if you look at regions where the average precipitation remains constant, doesn't change, there's no trend over time, but the annual distribution of rainfall is changing, like precipitation, number of rainy days, the clustering of precipitation during the year, because it's hard to separate the two, right? So I was wondering if you look at
yes. So we actually did this full statistical analysis with all 4 precipitation measures plus the fixed effects for the region and the fixed effects for the year and the error term, and that actually encompasses all of these effects. So if you have change in economic growth in one region, but you don't have a change in the annual mean precipitation, then this has to come from something else, right? And this method, which was invented by us, is actually accounting for these. It's not really doing a trend analysis or something like this. It's trying to use the full spectrum of the data. So yes, it's included. What you suggest, it's included in this analysis.
Thank you.
Smita, you had a question early on that now is maybe a chance to ask it.
Yeah, on the Levermann paper, right?
Yes. Mm-hmm.
Yes, I was just thinking of whether the assumptions underlying the models drive some of the policy recommendations, or just the damage function increases linearly.
Yeah, no, it's not. It's not.
For example, there's no
it's
threshold.
a very good question. Sorry. No, actually, I always show this. Sorry, I should do the sharing again. But to this end, I have to give me a moment. I show this plot just in order to illustrate this. But so here we do the sharing, and here we go. I show this plot just to illustrate it, but it's not. There's no assumption that the climate damages increase linearly. You can see just 3 illustrations here. It's the full curve is linear increase. The dashed one is a slight quadratic increase. It's not quadratic. It has a different exponent. And then we had a square root in. But in the actual analysis, this was actually from a paper. An earlier paper here, but in the actual analysis, we used the DICE model, which is the intertemporal, by Nordhaus, this intertemporal optimization method, and we put the Berkey et al. Damage function in there, and you can see, and so this is not that this cannot be captured by this kind of linear damage function approaches. So it's really the full regional Berkey et al. Damage function. Well, this one here. Well, no, I haven't shown it, right? Have I shown it? Anyway, it's this one here from the Nature paper. We put this one into the DICE model, and it then optimizes the path in the next 100 years, and you get basically a nonlinear damage function, and you end up independent of the socioeconomic assumptions, meaning how much do we value the difference? Well, how much do we try to avoid the difference between rich and poor? How much do we try to avoid? How much do we value future generations' welfare over the current welfare of society? Independent of this, you actually end up with these 2 degrees of warming or less, basically, and the reason is this simply. That's why I'm showing this always on the left. That's the basic reason. But there's no assumption about linear or nonlinear damage functions.
Thank you.
While you have the slide up, and I was going to ask you another question, which is, I think you said something about that this relationship or this conclusion holds regardless of.
Yes.
Can you say a little bit more about that?
Yes, and that's why I'm using. I show this. I mean, I should probably give a talk only on this paper, right? I just wanted to make this point, but you see, the mitigation costs actually have quite a universal shape, independent of how you compute it precisely, because it has to be at zero when you let climate change just evolve without mitigating anything. Right. So it has to be at about 5 degrees. It has to be at zero, and it has to be basically infinity at the current warming level. So this green shape is quite well. It's given. The different models that are used, integrated assessment models, they give different shapes, but they're basically always curved like this, and they go to infinity here and they're zero here. And now it's all. Now you add to this the climate damages. And what happened before with Nordhaus was the climate damages in earlier studies were so low that you would hit the green curve somewhere here, and there was actually there were high warming levels that actually gave the optimal warming. But the moment these damages become relevant and are not just a hiccup in the economic world, but they become relevant, and that's what happened with the Berkey estimate, for example, and with all estimates that are after that. The moment you really cross these the damages cross the mitigation curve much earlier. And it's not the crossing of the two lines that really is the optimal warming level. It's when you sum the two and then you look at the minimum, which you find here. But the crossing already indicates the problem, kind of. So the moment the damages are high enough that the optimum the optimal is actually close to the current warming level, and only if the damages are getting to infinity, you actually reach the current warming level, if you like. But it's a very universal response because of the shape of these two curves.
Mm-hmm. And is it just a lucky coincidence that it turns out to be 2 degrees Celsius? Yeah, that's what Paris decided on.
No, it's really not. I tried to write it in the introduction of this paper because I thought it's a very forceful argument. Let's look at this linear curve here. Only the solid ones, right? The solid green one and the solid red one is the damages. Now, in the Berkey case, this solid black one, in the Nordhaus case, in the earlier ones. This was way down here, and you can see that if you have a very shallow damage curve, because climate damages are very small, then you can actually have an optimal warming, the sum of the two, that is very, very high. But the moment you get up here, somewhere into a relevant level, the minimum of the sum of the two curves is getting closer to the current warming level. And because of the shape of the mitigation curve, you cannot really get to the current warming level because the mitigation costs are infinite. But you're pushing it close to the current warming level. And the current warming level is already 1.2 degrees. Mm-hmm. So 2 degrees is just in the vicinity. It's just, what everyone would think is true is also here computed. And that's the warming has to be as low as possible. Mm-hmm. That's basically what is to resolve from that. Mm-hmm. So I should really get a figure with less lines, with only 3 lines. These all dashed ones are really, not helpful, I feel.
Lynn Johansson, you had a couple of questions to our speaker, so.
Oh, thank you. Is your research connected to the world weather attribution work?
The world, no, it's not. Oh, sorry, there's a, no, it's not directly, no. It's the attribution of weather events is obviously very, very important. We did a bit of attribution of the precipitation signals that we find in the models and compared them to the observations, and thereby found that it's actually the CO2 that's causing the fingerprint of precipitation changes on the planet, which is not so surprising, but it's this is kind of an attribution thing, but nowhere close to what I think what you're referring to is for Federico Otto and people do. Is that correct? Who attribute weather extreme events to climate change. We don't do that. It's very, very worthwhile doing, but we don't do that.
Okay, thank you. My other question is, if I understand what you shared on slide 7, where you had the cost of emitting carbon, and you showed on the lower right-hand side a map which, and if I understand this correctly, the northern countries, Greenland, Canada, the Nordic countries seem to stand the opportunity to gain economically, where other countries may not be in that same situation. And does this assessment take into effect sort of the global exchange of goods? Because companies ship things all around, and if that were, or maybe is separate, but would this suggest then to some of the major companies that they should start pulling their supply chains, like their upstream supply chains, closer to the northern markets?
Yeah, that's a very good question. I mean, what you see here is the Berkey version of this, and you can see already the signal that you indicated. This is basically, let me just, this is the updated version by Calcul and Vence, which is showing you exactly the same, but with a higher resolution. And you see that the countries or the regions that actually gain from climate change are now very few, right? They still exist, but there are very few. And this is actually accounting for everything that happened in the past. So, because it's the last 40 years of data analysis. And so it would also incorporate any adaptation that has been taken place during this period, knowingly or unknowingly, including any effects on the supply from other countries. So what I keep kind of saying is that this would change if we take climate change into account, also when we think of where to produce and the supply chains and the supply disruption. So then this figure might change, and also obviously if we take the production sites closer to home, if you like, or put them into the blue regions. But in principle, this is all incorporated in this figure, everything that happened in the past. If you want to model this really if you want to model this and not see what the data did, then you would have to do something like this, which we are trying. Obviously, we have a major calibration problem because we have a lot of parameters, and we really need to find very well artificial intelligence also techniques in order to calibrate these parameters with the global markets, and we haven't done that yet. So it's really still a qualitative thing.
Mm-hmm. I think Lynn is wondering whether the simulation is available online. Yes, it is. Mm-hmm. Mm-hmm. But this is, but we
we only trust qualitatively in these simulations. That's the unfortunate thing. We don't really use it, and we never write papers where we say this is the amount of damage that you get from this model. That to this end, for this we only rely on the econometric analysis of the observational data. We eventually will have to bring these two together, but we are far from that yet.
So I think we have answered all of our questions and we're out of time, but thank you again for a really, really stimulating talk. And I think we're very grateful.
Thank you very much.